Today I'm going to talk about gluon and C inside the proton from a light from Hamiltonian approach. So this work has been done in a collaboration between our Institute of Modern Physics, and Iowa State University. So our name of the collaboration is BLFQ Collaborations. Okay, my talk has been divided into basically 4 parts. First of all, I'd like to introduce about the hadron properties, and then I'll talk about our theoretical framework is known as BLFQ, which is based on the light formalism, and then its application to proton. So in the first part of my talk, I'll discuss the proton structure based on this 2 Fock sector, going beyond to the leading Fock sector when we have one dynamical gluon. And the next part, I'll talk about with 3 Fock sector when we include one more pair, Q cuber, the C quark. So the talk is based on I'll talk about only GPDs, TMDs of gluon and C quark. And the talk is based on these 2 publications and our recent progress. So there is another talk tomorrow on BLFQ. Satpri will talk about this spin-1 system for gluon TMDs and quark TMDs. Okay, so there are 2 fundamental properties, mass and spin. So you all know that around 99% of the visible mass contained within nuclei, which is made from the proton and neutron. And they are again composite system made from almost nearly massless quark and the massless gluon. Just 1% of the nucleon's mass is coming from the quark mass. Then the natural question arises, how does this 99% mass come? So here is the gluon play important role. So the dynamics of gluon is very important to generate the proton mass. The another important property is the proton spin. We all know that proton is spin-off particle, but how does this spin, if we decompose this nucleon spin in terms of quark and gluon spin and their orbital angular momentum, that is not fully understood. From the experiment, our knowledge is that around 25 to 30% is coming from the nucleon spin, and gluon spin contribute around 40%, but there is a huge uncertainty at small x region. But our knowledge on this quark and gluon orbital angular momentum, that is not fully understood. There is some process proposed that gluon orbital angular momentum or quark orbital angular momentum can be measured. So I'll talk about all these things. So the thing is that there are 2 famous spin decompositions proposed. One is like frame independent, proposed by G. It's talk about that there are 3 parts, basically the quark spin, quark orbital angular momentum, and the total angular momentum of the gluons. So all this quantity can be obtained from the GPDs at the leading twist GPDs. If you know that, you can calculate all these 3 quantities. Another decomposition is the Jaffe-Monod decompositions. There are a lot of talks in these workshops. So there are 4 components basically: gluon spin, gluon orbital angular momentum, quark spin, and quark orbital angular momentum. The problem is that this is the canonical orbital angular momentum. To calculate these things, you need some higher twist operator, or you need like higher twist GPDs. From these lattice calculations, we know that around 42% coming from the total angular momentum coming from these gluons, and this is for quarks. This is for U quark, I think this is for gluon, and this is for D quark. And this gluon spin around 0.3 from these lattice calculations. So to understand all these things, first of all, we have to understand the tomography. We all know these things. So there are 2 main distribution functions. One is momentum space called TMD that can talk about the probability of finding a proton with longitudinal momentum fractions and the transverse momentum. But they don't talk about any position informations. On the other hand, GPD will provide you some longitudinal distributions as well as the transverse positions are part. So if you combine these 2 quantity, we'll get more a general distribution is called Wigner distribution, which is like H-phase distributions. So after if we certain phase-phase reductions, you will get TMDs and GPDs, and further reduction, you will get one-dimensional distribution, ordinary Proton distribution function, or the form factor. So all these quantities are going to, GPDs or TMDs, they are, EIC is going to measure all these things. So it is quite interesting to study, definitely. So now I'm going to talk about our theoretical framework. Is known as basis light-on quantization approach. It's a computational framework, first of all. is based on light from Hamiltonian approach. So what do? We write down this equation is like Schrodinger-like equations on the light front. If you know the light from Hamiltonian, then you can solve it and get the eigenvalue and the eigenvector. So eigenvalue corresponding to the mass square term, and the eigenvector that will give you the information of the structural information of the bound system. So P minus is just like light from Hamiltonian, and P plus the light from longitudinal momentum. So after solving these things, I mean, you have to know this light from Hamiltonian by derived from the first principle, or you can model it. So once you solve these things, you get the light from wave functions, and once you know this light from wave functions, you can study many properties. So our target is to see proton spin and proton three-dimensional structure, like calculate the form factor, GPDs, and TMDs, all this stuff. Okay, so let's say what we do, we first expand this proton or hadronic state in terms of Fock space basis. So for example, if you write down this proton state in terms of leading Fock sector with gluon, with C quarks, so you can also expand further. So we use two-dimensional harmonic oscillator basis in the transverse directions, and the plane wave basis in the longitudinal directions. So if we identify one particle in the Fock space, we need 4 quantum number. First is the longitudinal quantum number, K, we denoted is by K, and this N and M, these are the two harmonic oscillators, the principal quantum number and magnetic quantum number. And lambda is assigned for this helicity of this particle. So if we have the many body, because there are in Fock sector there are a lot of particles, so the many body state can be written in terms of like direct product of the single pattern basis state. So since it's a numerical approach, you have to truncate your basis in some way. So in the transverse direction, we truncate by these equations, or this n max we call transverse truncation parameters. And if we sum over all the momentum, that will give you like, we call sum over k, that will give you k. So if you fixed n max and k max, that means you fixed your basis size of your system. So what is the advantage of this approach? So first of all, we have this rotational symmetry. I mean, of course, if you truncate your Fock space, the rotational symmetry is already broken, but the broken is not so severe. A second is that if we increase our Nmax and Kmax, we have correct UV and IR cutoff, and we also get exact factorization between this intrinsic pattern motion and this center of mass motions. So that is the advantage of this approach. Now I'm going to talk about the history, little bit history about this nucleon within BLQ. It started in 2020. So initially we used just model parameter. I mean some effective Hamiltonian. So where we have like kinetic energy part and this confining potential. This confining in the transverse direction, we use this confining potential from light from holography. And in addition, we have some longitudinal confining potential. And kappa, the strength of the confining potential. And to get the spin structure, we have another kind of interaction, it's called one gluon exchange interactions, where Q is the exchange of this momentum between these two quarks. So if we solve this Hamiltonian, we obtain this wave function in the further study all these properties. So these are the recent publications based on this Hamiltonian. But my talk is based on the gluon and C quark. So to get the gluons, we have to include gluon in some way. So we expand our Fock space. So we have like two Fock sector with one dynamical gluon. And for this, since we have these two Fock sector, there is a possibility to include like QCD interaction now, instead of some kind of ad hoc one gluon exchange interactions. Okay, so for this two Fock sector, we have the possible interaction like the vertex interactions and the the instantaneous gluon exchange interactions. And this is the corresponding light from Hamiltonian. But this is not enough. Still, we need some confining potential in the leading Fock sector. For that, we use the same kind of confinement that we used in the leading Fock sector before. So these are the parameters we set, the quark mass, and we also have the gluon mass and the strength of the confinement to fix the proton mass and the electromagnetic properties of the proton. So by solving with this harmonic oscillator basis and the longitudinal basis, we obtain the wave function and further investigate all these properties. So for example, okay, so now basically what we have this kinetic energy term, we have the confinement in the leading Fock sector, and the vertex and the instantaneous gluon exchange interactions in the Hamiltonian. So once you solve this Hamiltonian, within in these two Fock sector, we have the probability of the, we found that the higher Fock sector, the probability of this higher Fock sector is 56%, and the 44% is coming from the leading Fock sector. So we have now wave function with gluon. So we can investigate all these properties based on this gluon. Okay, so this is the helicity PDF based on our basis light from quantization wave. So this is for quark helicity. This is for gluon helicity, and these C quarks, they are solely generated by these scale evolutions. So we found that if we see the red band is BLFQ without the gluon, and blue band with the dynamical gluon. So we see that small x region, there is an improvement, including this gluon, dynamical gluon. So the D quark is quite good in agreement with this global fit or the experimental data. And for this gluon case, so we found that our result is more or less consistent with that global fits. So since we have this helicity distribution, we can calculate the gluon spin or quark spin, and we found that gluon spin contribution is around 26% of the proton spin. Okay. The next is the helicity. So the ratio of these polarized to unpolarized distributions, and again we can find that this our result for D quark is quite good in agreement, but it's still negative. But U quark is going to, I mean, this expected behavior is going to up, going to 1 basically, and this is for gluon case. So this is the but if we compare with this light from holography case, we can see that there is a transition at point A, x equal to 0.8, and it's going to positive to 1. But we didn't find that features. This is the different from this light from holography case. Okay, so since we have these wave function, then we can also calculate like gluon GPDs. Gluon GPDs, can be parameterized. I mean, the gluon correlation function can be parameterized in terms of this is for unpolarized gluon. We have this gluon GPD H and E. For the circularly polarized gluon, we have another two GPDs, and we have calculated the GPDs using our wave functions. And of course, the result I'm presenting here at the model scale, we didn't evolve this. So our initial scale is around 0.25 GeV square, so which you obtain by matching the moment of the quark PDF at 10 GeV square after the scale evolutions. So this is for H, gluon GPDs H, which we found that the distribution look like is positive, and this is negative. H tilde is positive. Since we have all this GPD, now there is a possibility to calculate the total angular momentum of gluon. So total angular momentum from the G sum rule, we can calculate these things, and we found that this is the result, 13.2%, the total angular momentum to the proton. Okay, so now we can talk about the spin decomposition. Hatta was talking about these things. So we can calculate the spin, we can calculate the gluon spin, and this is the total angular momentum, and this is the kinetic orbital angular momentum can be calculated by subtracting this total angular momentum minus of the spin part. So this, if you see this result, we found this is the corresponding result. I mean, the quark contribution is 72% at the model scale I'm talking about. The gluon will contribute 13.2%, and orbital angular momentum of the quark, the kinetic orbital angular momentum is around 15%. But if you want to calculate the canonical one, we calculate this from this GTMDs F14. So we calculate these things, and we found that again the spin is same. The spin of this gluonic contribution is like 25.4%, but there is a cancellation between quark and the gluon orbital angular momentum. So the percentage is very small in that case, the canonical decompositions. Okay, so another interesting quantity is that if you want to see the radius of the quark and gluon inside the proton, so that can be calculated using the unpolarized GPDs. So unpolarized GPDs, if you using this formula, we can calculate the x-dependent square radius, and we found that at small x region, so gluon is like the radius of gluon is greater than this the quark distributions. So, and if the proton takes if we increase the proton momentum, basically when x tends to 1, this proton is behave like a point-like particle, basically. So at this region, it is expected because gluon is dominated at the small x region, so the radius would be the large at the small x regions. And using this formula, we can calculate the square radius, and this is our result. B square is like 0.47 Fermi square, or the extracted value is like 0.43 Fermi square. Okay, so now I want to talk about a little bit the gravitational form factor. So gravitational form factors appears when graviton interact with the proton, but the problem is that the gravitational interaction is very small compared to the electromagnetic interaction. So the graviton is not detected yet in the collider. It is important because if you know the gravitational form factor, then you can calculate many other properties like momentum, mass, momentum, and the mechanical properties like pressure, shear force inside the proton. Interesting thing is that graviton is spin 2. If we, when it's interact, the proton momentum changes, right? So this process can be mimicked in this DVCS process, where a virtual photon interact with the proton, and its same is a real photon. So effectively, so the total spin, because of the 2 photon, we have also spin 2. So this process can be mimicked through DVCS process. So that's why people can extract the gravitational form factor through this process. And JLab have extracted the D form factor for this gravitational form factor, for D term, basically. Okay, so gravitational form factor can be calculated through this matrix element of energy momentum tensor. So if you know the energy momentum tensor, we can calculate this matrix element, and that can be parameterized in terms of 4 gravitational form factors, A, B, C, and C bar. So this is very important things because they follow some sum rule. The first one is the momentum sum rule. If we sum over all the A0 at, that should be the total momentum of the system. That should be 1. And the gravitomagnetic moment sum rule, I mean, at q square equal to 0, if you sum over all the B form factor, so that should be vanished. And this is true for each Fock sector, leading Fock sector, higher Fock sector, or any other Fock sector. If you have all the particle, if you sum over, that should be vanished. And using these 2 sum rule, there is other sum rule that's called spin sum rule proposed by G. So that is the sum over A and B. So we can, so from this A, B, and AB, or this form factor, we can know about the momentum, spin, gravitomagnetic moment, all these kind of things. So there is other sum rule. It's called based for this form factor C. If you sum over all C0, that should also be 0. That is because of this conservation of energy momentum tensor. So and another form factor, this is what is called this D term, which is 4C, that provides all these mechanical informations. So in our case, we know the wave functions, we know those energy momentum tensor, so we can calculate all these things. So these are the result. This one for U quark, this is for D quark, gluon is for green. The green is for gluon. So if we add them, we can see that the momentum sum is satisfying in this case. So, and then for the case of B, we can also see this is for U quark, this is for D, and this is for gluon. So if we add them, the black line basically, the total at q square equal to 0, B is also 0. So yeah, so from this is our initial scale result, and we can also calculate the D term, and these 2 form factors are obtained by this matrix element of plus component of energy momentum tensor. So another form factor is, this is the D term form factor. So this is one of our new result actually. So we can see there are a lot of lattice calculations, and this red dot is the experimental extractions. So we compare our result, we found that this is more or less consistent. So this form factor negative is because of the stability of the proton. If you want to calculate the pressure, you can find the inside is pressure is positive, outside is negative, and effectively total pressure is 0. So yeah, this is the result from the BLFQ calculations. So yeah, there are a few talks on this gluon TMDs. So I just want to talk about a little bit our result on this gluon TMDs. So gluon TMDs can be obtained from this what is called these gluon correlation functions, and that can be parameters in terms of 8 gluon TMDs. 4 of them are T even, and 4 of them are T odd. The gray band, these are the T even case. So we just calculated the T even TMDs using our BLFQ wave functions. So I just want to show this result. First, this is the gluon TMDs for unpolarized case. So this is the three-dimensional structure with x and k power square, and this is the cross sections of these when for fixed values of x. We see this is the F1. This is for, I think this is for G1L, G1T, and this is the H1 perf. So we see that there is a transition for this H1 perf positive to negative, and this is the cross sections of X across in when K perf is fixed. So another important thing is that our calculation satisfies all this positivity bound. I mean, all this mentioned here. So this is coming soon, actually. Then another property is that when we can check also the large X behavior, large X or small X endpoint behavior. So this endpoint behavior. So if we take this ratio, that should be 1. So if we can see from this plot, if we increase our basis size in the longitudinal directions, that means it's going to 1. So effectively, it will satisfy the condition. And on this helicity asymmetry, at the endpoint, it should vanish when x tends to 0, and the ratio is going to 1 when x tends to 1. So again, if we increase our basis size, so that means it's going to 1. I mean, we can see this kind of trend. So if we increase more and more in the longitudinal space, so that is effectively satisfy this condition. And now another important quantity is that whether our TMD satisfy the Gaussian answers or not. If the conclusion is not, because you see, so if we assume if it is Gaussian answers, then this quantity, if we calculate the expectation values of k square multiplied with these k zeros and divided by these expectation values of k, so these quantities should be 1 for every values of x. But from this figure, we can see, okay, it's not, nowhere it is going to 1. So this is like polynomial kind of things. So the conclusion is that BLFQ results do not support the Gaussian answers. So this is the result for the k square expectation values as a function of x. And we found the peak, the maximum value is x equal to 0.5. Okay, so there is a discussion on this twist 3. Since we have the quark and gluon in our pictures, so definitely we can calculate the genuine twist 3 TMDs. So these are the result. For this, this is the result for the leading twist, just 8, or the T-even, just T-even 6 leading twist TMDs. And these are the total twist 3 TMDs, and this is the genuine part. Since we have this gluon in this picture, so we can calculate the genuine twist 3 part. And we can notice that twist 3 distributions is quite large compared to this. I mean, it's comparable with this leading twist distribution, so it is quite important. So I just want to mention these things, and it's concentrated near the small x, small k perf region. Okay, so why twist 3 is important? Because twist 3, if you know this twist 3, we can calculate all these asymmetries. I mean, the these blue colors, we can calculate using the twist 3 TMDs. And the question is that EIC, it's quite difficult to extract twist 3 TMD in EIC or EICC. So, but here is just a model study to extract this asymmetry, because there is a suppression for the twist 3. So if your energy is too high, then you cannot detect like this kind of structure function or this asymmetry. So here is a comparison between EIC or EICC's case. For EIC's case, energy is a little bit low. So it's possible. I mean, if we see from this figure, the comparison between this is the result for EIC kinematics and this is for EICC. This is for EIC, this is for EIC. Black line is for EIC's case. So yeah, we can see the difference if we have this energy difference. Okay, so now the last part of my talk is just, now our main goal is to solve the Hamiltonian without any confining potential, just based on the QCD interactions. So that's why we completely remove the confining potential. But since we have this like 3 Fock sector, like leading Fock sector, gluon, and this C-quark Fock sector, so we have this opportunity to include more and more QCD interactions. So previously we have just these 2 interaction now we have this because, okay, so just because gluon can split into like quark antiquark pairs, so we have this interaction. We have also instantaneous fermion interactions. So we again solve this our full Hamiltonian without any confining potential, and obtain our wave functions. And for this case, we have like this Fock space decomposition. Now we have like 53%. This is the probability of leading Fock sector. 26% is the gluon Fock sector, and 20% is this C-quark Fock sector. And from the C-quark Fock sector, UU bar and DD bar, these are the same, more or less. And this is for SS bar is very little contributions. So effectively, we have this wave function with gluon and C-quark, so we can calculate again the C-quark and gluon distributions inside the proton. So this is just result, preliminary result when GPDs for C-quark inside the proton, and we notice that this is for U-quark, 8 GPDs, this is EGPDs, and DD bar. So we notice that all these GPDs are concentrated near this small X region. This is obvious because the C-quarks is dominated at the small X region. So this is expected behavior from this C-quark GPD when skewness is 0. Although we have now recently, we have calculated the non-zero skewness result, but I'm not showing here. So this is the C-quark TMDs. This is a very recent result. Again, we have noticed that only these two are dominating, other are very small. This is, of course, as very small p per square region. So these are the result basically. This is for, I think, D quark for X, or when p per fixed. This is with respect to p per square when X fixed, and this is for what is called UC. And the final slide of this, like this asymmetry of this D bar to U bar asymmetry, the behavior is we obtain this behavior. Okay, I would like to conclude my talk. So basis light from quantization approach, a non-particular approach based on the light from Hamiltonian. So the idea is that you have to know the Hamiltonian of the system and then solve for it within some basis. We use transverse two-dimensional harmonic oscillator basis in the transverse directions, and the longitudinal directions we have plane wave basis. And after solving this light from Hamiltonian, we obtain the wave function and then calculate all the hadronic observable. So for this presentation, we have just considered this leading to Fock sector with confining potential. And for this case, we don't have any confining potential. So that provide, I mean, within this case, that provide good description of the global data. And we have also calculated the spin decompositions. The 70% is coming from the quark spin, 26% is coming from the gluon spin. And okay, so outlook is that this interaction is not enough. We need to include more and more interactions, like 3 gluons or 4 gluon interactions. So I just want to mention this is not the complete picture. Long way to go. Thank you for your attention.
Thank you.
To include confinement, people usually change the propagators. They do not take the naive propagator, but these discussions about revolve propagators and all. So can't it be included in the slide from formalism instead of including a potential? Or
yeah, okay. So we have two kind of potential. One is the transverse directions, which is directly coming. We know the potential should be like harmonic oscillator type potential, which people already solved in the light from holography. We just adapted it. And we also know the longitudinal potential, but in the non-relativistic limit, it also gives some one-dimensional harmonic oscillator potential. So basically, we have 3D harmonic oscillator potential. So we don't use any propagator form.
Yeah, so nice talk and nice results. Thank you, Chandan. I had some questions concerning the higher twist. The first one is, to which extent your calculations fulfill the equation of motion relations? Because it's not clear to me that if you have a model which is not really PQCD, are you sure that then your results fulfill the equation of motion relations?
Yes, yes.
Can you check it?
Yeah, we have checked this. Yeah, from this, we obtain this relation from this equation motion, for sure. We check these things.
Okay, thank you. And then to do predictions for semi-enclosed DIS, you need also the fragmentation functions.
Right.
What are you doing with the fragmentation
Oh,
functions?
yeah, that is, sorry, I may not, yeah, I didn't mention here the fragmentation. Oh, yeah, we have taken from this literatures. So there is already some form of this fragmentation functions. I forgot to mention. Sorry for that. Yeah.
But you're taking only, I guess, like D1 and Collins function.
Right,
I don't
right,
think
right.
you have any information on the subleading twist fragmentation.
Right.
Okay, okay.
Right.
Good, good, good. And if you allow me, I have also another last question. How do your results for higher twist compare to other model results or extractions? Do you have some comparison with some other calculations?
For which observable, for example?
Twist 3 in general, maybe the E of X or maybe something
because
else.
for twist 3, with genuine twist 3 part, I didn't find any result in the literature yet. So I don't know. I think you have calculated only without gluon. You don't have any gluon in your picture. Well, I don't know then. That's good if you have.
And for the, let's say, not pure twist 3, but just a twist 3 kinematic, do you have any comparison? Just to have an idea if they are similar or if they are entirely different. No, you don't have a comparison.
Yeah, because this is very new, this result is very new, I think. I mean, we didn't compare with this. If there is any available result in the literature, definitely we are going to compare. I have to check that for. Yeah.
Maybe you can compare it to some Vanzura-Wilczek-like results.
Okay.
Are you strongly violating any Vanzura-Wilczek relation?
Yeah. Right. I mean, for this case, you don't have this H term, right? And we have this result. This is. I mean, if you know this F1 is comparable, then of course this E of X or other higher twist TMDs that will be comparable. And our result is consistent. I mean, leading twist result is consistent with other available result in the literature.
Yeah, so but basically, if you take the E, the fact that you have a sizable E tilde means already that you are breaking the Vanzura-Wilczek.
Yes. Yes.
So you're breaking Vanzura-Wilczek all over the place.
Yeah, I mean, if somebody has genuine twist 3 calculation, definitely that will be very good to see the comparisons. Okay. I'll check that for sure.
Who's the next speaker?